Welcome to the last part of our discussion of thermodynamics. In this lecture, we're going to talk about the three methods of heat transfer, two of which will be heavily applicable to our situation, but for the sake of completeness, we want to talk about all three. The first one, which won't apply to us much, is the convection. Convection is the method of heat transfer by means of a macroscopic migration of particles from one region to another region. What's important here is that the particles physically move and change position. They move from one point to another physically. An example of this is you just consider when wind blows, a cold wind. What happens is that a body of particles which are displaced and replaced by colder ones. That's why when cold wind blows, we immediately sense the change of temperature because there was a heat transfer by means of migration of particles from one position to another. And this is the same principle that's employed in air conditioners. What air conditioners do is they replace the air which is present in a room with particles that are that have a lower temperature. That's how air conditioners work. And over here, another example I have for visual purposes is that of boiling water. If you have water on a pot and you're boiling it, the part of the pot that's immediately in contact with the fire usually gets quite warm, much warmer than the surface, and as a result, the particles at the bottom, they become lower in density and they begin to rise. You may have heard the expression of warm air rises. So basically the particles at the bottom that are in immediate contact with the surface at the bottom of the pot, they begin to rise, and because they rose, the particles which initially were at the top, they are slightly cooler. They descend to the bottom. This kind of a actual migration, movement of particles from one position to the other is called convection. And it's one of the modes through which heat could be transferred. What's important with convection, or what we need to take note of, is that convection always requires the availability of particles that can migrate. This is quite important. Convection requires particles that are mobile, which can actually move from one point to another. Let's move on to the second method of heat transfer. This is quite important and it's quite familiar to us also. Here we have a heat transfer. This is conduction. Conduction is a heat transfer by physical contact through matter or particles that are microscopically stationary. Contrast this with convection, where the particles were actually mobile. With conduction, the particles do not move, but what's important is that they are in contact. This is the reason why when you have a cup of coffee which is hot, you touch that cup of coffee, although there are no particles moving physically from the cup to your hand, but heat is nonetheless transferred. The means through which heat is transferred from the cup of coffee to your hand is by convection. That's because internally the particles of the cup are in contact with the coffee, which is hot, so heat is transferred from the coffee to the cup and from the cup to your hand. What's important here, or to take note of, is that we require the presence of particles. This time they don't have to be in motion, they don't need to be mobile, but these particles have to have physical contact. You may have this is quite common. You might be stirring a stew on a stove. After a while, the spoon you're using to stir the stew eventually gets hot to your touch. That's because there's physical contact between the stew and the spoon, and between the spoon and your hand. This is why we have to wear oven mitts to take out things from an oven. So this method of heat transfer is very, very important. It's going to be quite significant in how we treat our X-ray tubes, because X-ray tubes, they have this method of heat transfer is quite common, because a lot of heat is produced when we make X-rays. So this method of heat transfer is applicable to radiography. And actually, moreover, conduction as a means of heat transfer, it is able to explain why some particles, or rather some objects, at least to the touch, they feel cooler than others. For instance, metallic objects, every time you touch them, even though they're at the same temperature as everything in the room, every time you touch a metallic object, it will always feel somewhat colder than, say, a wooden substance or a substance made out of plastic. The reason for this is related to the rate of heat transfer. It is not necessarily that the metallic object is cooler, but it's that whenever you come into contact with it, there is a rapid transfer of heat from your hand to the object. That is why we sense the sense of cool is just us registering the quick heat transfer. This then brings us to the idea of the rate of heat transfer through conduction. The rate of heat transfer is simply the amount of heat transferred per given time. And this is what we have over here. It's Q, that's heat. T is time, lowercase t is time. The rate of heat transfer through conduction is given by K times A multiplied by the difference in temperatures between the hot object and the cold object. Remember, in order for us to have heat transfer, the first has to be a difference of temperature. And if there's a difference of temperature, a non-zero difference of temperatures, then heat will flow from the hot object to the cold object. So it shouldn't be a surprise why we have the temperature of the hot object minus the temperature of the cold object. So the metal, so imagine again, you are coming into contact with a metal object and your body temperature is 36 and the object is at room temperature, the metallic object is at room temperature, say 23 degrees Celsius. When you touch it, because your temperature is higher than that of the object, you're going to experience a heat transfer. This heat transfer will depend on not only the differences in temperature, but it will also depend on K and A and D. I will mention this later, but K is a property of the object in question, or the means through which the heat is being transferred. It's referred to as thermal conductivity. That's what K is. It's a measure of how well an object can conduct heat, can transfer heat by means of conduction. And A is simply the surface area. So if we're using our whole hand to touch the object, then the surface area would be, A would be the surface area of our hand, the part that's touching the object. And D here refers to the thickness of the object, or rather of the part that's the thickness of the surfaces that contact each other. The picture after this will make things clear. So pictorially, we might imagine that there is our hot object and here's our cold object. But these two are put into physical contact through some other object here, and We know that heat is going to flow this direction because this object has a higher temperature than this object. But how will heat move? How will heat travel or be transferred from this object to this? It will be transferred through this object here. Now, obviously, since this object is the bridge through which heat could be transferred, the size of the contact here dictates how much heat we could transfer at a time. So this contact patch here between the hot object and the cold object is what we mean by A. That's the surface area of contact over here. Now, also, the length of this object will dictate how fast we can transfer heat. For instance, if you are stirring a soup with a short spoon, it won't be too long before you start to feel the spoon getting hot. But if you were using a longer spoon, it will take you a lot more time for your fingers to sense that, okay, the spoon is now getting hot. That's because the rate of heat transfer by conduction depends on this distance here, how long this mediatory object is. The object that mediates the contact between these two objects here, hot and cold objects. So this is what this equation refers to. Let's quickly recap. Q refers to heat, T refers to time. So this is it's the amount of heat per given time. This depends on the thermal conductivity of this object here. The thermal conductivity of the object which is mediating the physical contact between the hot and the cold object. And the surface area refers to the contact patch between the mediating object and the hot and also the cold. And of course, the difference in temperatures will dictate in which direction heat flows. Because this is hot and that's cold, we know heat is going to flow in that direction. Although here in this diagram we have T2 and T1, and also in the textbook it might use T2 and T1, be careful. This is not referring to final minus initial temperatures, but it refers to the difference between the temperature of the hot object and the cold object. Okay. We will do more examples on how to use this formula, so do not be bothered so much by it. And we'll have more discussions about it. Okay, this then brings us to most probably the more important mode of heat transfer, and this is through radiation. So radiation is nothing more than a heat transfer by either an absorption or an emission of electromagnetic waves. This method of heat transfer is quite unique in that there's no need of mediating objects, there's no need of physical contact, there's no need of even matter particles to migrate from one point to another. Actually, all we need is space-time. As long as there's space, electromagnetic waves will move from one point to another. Basically, electromagnetic radiation only needs space. It doesn't need a medium through which it can propagate, except for space-time. Okay, an example where the method or where radiation as a means of heat transfer is involved is when we switch on our heater on a winter afternoon. Although we don't touch the heater physically, and there's no air that's being blown by some kind of a heater fan. I'm thinking of a regular heater that's just electric heater. But nonetheless, we still get the sensation of warmth. How does this occur? How is it that there's heat transfer between the heater and us? Well, this occurs because of radiation. The heater is emitting electromagnetic waves, and these electromagnetic waves are absorbed by us, and as a result, this affects our temperature. The same is true of a campfire. We don't have to touch a campfire to be warm. We just need to be in the vicinity. The closer we are, the more we will sense the heat. But the farther we are, the less we will sense the heat. But we nonetheless will be under this. We will receive some radiation. Another situation where there's radiation involved, you could think of the relationship between the Earth and the Sun. We know that space is approximately empty. It's a vacuum. However, the heat from the sun is able to warm up the Earth. How is this possible? It's because of radiation. And of course, our microwave ovens, although they sometimes heat up the plate instead of the food, but nonetheless, the means of heat transfer in the context of microwave ovens is radiation. Now, with radiation, there is an important fact, and that is all objects, no matter what object it is, all objects both absorb and emit radiation. As we speak, you are emitting radiation to the environment, and you are at the same time absorbing radiation from the environment. So it's quite important for us to take note of this. It's going to be useful. I will repeat it later on, but this concept to realize that not only are we the recipients of radiation, but we are also sources of radiation. Now, how fast is heat transferred through the mode of radiation? Well, for this, we need to go to Stefan Boltzmann's law of radiation, and this law tells us that the rate of heat transfer by means of radiation is equal to sigma times epsilon times A times T to the power 4. Let's talk about what these symbols mean. Q still serves as heat, so that's the amount of heat, and T refers to the time, the amount of time it took to transfer that amount of heat. So this is the rate of heat transfer. Sigma is a constant. It's a number which has been determined through experimental means. It's fixed. It's called the Stefan Boltzmann constant, and it's given by this. Epsilon is what is known as the emissivity constant. All it does is it measures how well an object can either absorb or emit radiation. Some objects are very good absorbers, which means they are very poor at reflecting. Other objects are very good reflectors, which means they're very poor at absorption. For instance, think of a mirror. A mirror is a good reflector. That means it's a poor absorber. So it doesn't absorb waves, electromagnetic waves as well. So this epsilon would be quite small for such an object, for a mirror, for instance. But objects that are very good, like objects that have a black color, they are very good at absorbing radiation. And as a result, their emissivity constant is quite large. And I should specify that the emissivity constant is a property of an object, and it is always limited to this interval. It is larger than 0, or larger or equal to 0, or less than 1. It is never large. It is never negative, but neither is it larger than 1. If you'd like more information about this, I'd be happy to talk about it more. And then A, again, is the surface area of the object we're dealing with. If we're interested in the amount of radiation by, let's say, a spherical ball, then A would be the surface area of the spherical ball. If we're interested in the amount of radiation absorbed or emitted by a rectangular block, then the surface area, A here, would be the surface area of that rectangular block. And finally, we come to the last parameter. This is temperature. Here, temperature refers to the temperature of the object we are discussing. If it were a sphere, then we would be asking about the temperature of the sphere or of the block, or maybe sometimes of the environment, if we're interested in how well the environment is emitting or absorbing radiation. But here's what's very, very important, and most students tend to make this mistake, and that is the temperature here is always in kelvins. When we speak about radiation, or when we seek to determine the rate of radiation using the Stefan-Boltzmann law, it is important that we remember that our temperature must always be in kelvins. Please remember that. Okay. Now, let's go back to what I said earlier, this important thing here, this important fact. Because objects are always emitting and absorbing, in order for us to truly determine how much heat is being transferred to the object, we need to find the difference between how much has the object absorbed minus how much has it emitted. Let's go away from this example. If I truly want to find out how much money have you made, imagine we're talking about money. If I truly want to find out how much money have you made, because we're always, all the time spending, I have to determine how much have you gained and subtract from that how much have you lost or how much have you spent. That will tell me the net amount of money you have gained. I hope that little detour is helpful for you to understand this part. Is that the net rate of radiation is equal to the rate of absorption. In other words, how much has how fast is the object absorbing minus how fast is it emitting. The outcome here will tell us the net rate of heat transfer by means of radiation. Okay, so now what is it that affects the rate of absorption? Consider an object like this. This object has temperature T OBJ, that refers to object, and this object is placed in an environment whose temperature is TENV. The ENV refers to environment. What the object will absorb depends on the surrounding temperature. If the temperature of the environment is TENV, then the rate of absorption by this object is going to be this. It's going to be the sigma, that's the Stefan-Boltzmann constant, and epsilon, that's the emissivity constant of this object, times the surface area of this object. But then for the temperature here would be the temperature of the environment. Because remember here, we're focusing on the object absorbing. So in other words, we have to ask how much is the environment, what is the temperature of the environment? So this part is the part of the rate of absorption. But then we have to subtract from this the rate of emission. Now the question is, how much is this object emitting? Well, the rate of emission depends on the temperature of the object itself. So again, we will have sigma, again it's a constant, Stefan-Boltzmann constant, times epsilon, that's the emissivity constant of the object, times the surface area of the object. And this time the temperature is no longer that of the environment, but that of the object, since we're interested in how much the object is emitting. And if we clean this equation up, what we're going to end up with is something that looks like this. That is the net rate of heat transfer by radiation is given by sigma times epsilon times A times the quartic temperatures, the difference of the temperatures to the power 4. By the way, I should mention many pitfalls that many students have of notice over the years is that sometimes students, in an attempt to simplify, they have done something like this. That's the T environment. minus T obj, and they have made this mistake. Please, this is not true. It is not true that the difference of the fourth powers is the fourth power of the differences. Please be careful. Do not avoid this pitfall. Okay. This concludes our discussion of thermodynamics, and for further reading, I would refer you to OpenStax, sections 14.5 to 7. These are the sections that pertain to our discussion, and they conclude our discussion of thermodynamics. And again, what would follow are examples on how to use these formulas to get a grasp of what they mean.